actually the reason why I like
This
reason why
meeting
I
is
like
being recorded.
the reason why I like Zoom is partly because my computer has quite little storage. So whenever I record to the
Oh
cloud,
yeah, because of the cloud, right, or something.
yeah,
Why
that's
don't, wait. Why don't you just connect like external SSD to record to?
uh I could, but it's just more convenient, honestly. But
Okay,
yeah,
I mean that works also. Although like, because usually I just don't trust cloud storage providers and not lose my data or like not
yeah,
spy.
yeah. But I'll just download it and upload it. So onto
Yeah,
from the
cool.
more
Fine.
beefy computer. Right, so today we'll talk about linear algebra, I guess, a bit
Yeah,
of it. So the central question today is the one that you sent me, which is if M is a map from V to W, V and
yeah,
W being vector spaces, how do I show that M transpose is a map from V star to W star?
right.
Okay. I haven't really exactly thought this exact through all the way, but I think I got some idea of roughly what's going on, and I'll just try to share my perspective.
Okay, sure, yeah.
So vector V when it's a basis, when there's a basis, when there's a basis for V, then
This V equals
you can
to
express any element of V as a column vector, correct? Yeah.
yeah, yeah. Well, I mean, I don't really think of it as like column vector, but like yeah, like
Mm,
just like isn't it just like if you have a basis, just a linear combination? Like if you have like everything's just
yeah.
a linear combination of stuff from the basis.
Yeah, I guess so. So for example, this
V
will roughly correspond to the
heck
okay,
my
it seems like the eraser is not working very well, but oh well. I'll try not to make so many mistakes. So this roughly corresponds to V. That actually immediately corresponds to V equals to E1, uh, E1 plus V2, E2 plus
okay,
so
so
on.
V has an element of V.
Okay, so
Confusion here.
right now when people talk about a basis for a V star, so V star is a space of all maps
Right.
all maps from V to the underlying field, which let's say is the complex numbers.
Uh-huh.
Then, so when people have a basis for V star, usually, okay, so how do we get a basis for V star? Usually it's induced from a basis on V. So when it's usually induced from the E1 and E2, all those so on. So usually what that means is that they will choose a dual basis, which let it be F. So they choose Fi
Fine.
such that F
Wait, stop. What do you mean by induced from here?
okay, so they'll choose it such that Fi, when mapping the EJ basis vector, is equals to the canonical delta. So such that like
You know
F1 of,
what a canonical delta is. Can't introduce that notation. What is
okay,
it?
fine. The canonical delta is equals to 1 if I equals to j and 0 if I not equals to j.
Oh, okay. So basically just like sets it, like just basically nulls out the stuff that
Yeah. So for
okay.
example, F1 would be the basis vector for V. F1 will be the basis
Oh, so
vector.
it's like the projection. So like it's
Yeah.
kind of like a projection map. Like
Yeah, exactly.
okay, right.
So F1 of E1 is equals to 1, F1 of E2, and anything else, right? Any other E3, E4
Yeah, zero, yeah.
or 0. And what
That
this
makes sense, yeah.
what this gives rise to is if suppose you have a element of V star, right? Let's let it be L, meaning linear map from V star to from V to C. So
Right.
L is a map from V to C. Um, and 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 so you can express L in terms of the basis vectors, the dual basis, right? The dual basis for V star, meaning that L is equals to, let's just say L1, L1, F1, L1, F2, and so on. So
All right.
um
Yeah,
L1,
EV stuff. Oh, okay. I kind of get like the toppling over analogy, right? Because like it's kind of like the dot product. Because you
yeah,
think
yeah,
it sends it to a scalar. So like if you do a like if you convert a column vector to a row vector, it sends it to
exactly,
a field element. Yeah, that makes
exactly. So that makes sense now because now when you consider LV, right,
right.
then this gives me a complex number. How do I construct it? I do the linear thing, F1 plus so on, Ln, Fn, and I map this entire thing to E1, V1 plus, sorry, V, it should, V1, E1, I shouldn't make the notational V1, E1, so on to Vn, En, where n is the dimension of the
Sure. Yeah.
and this just equals to when I expand it out, it just equals to L1 V1. So L1 V1 L plus so on to L and Vn. So this
Wait, sorry, one sec. The L, the little L, whatever thing, is that like you're composing the maps here, right? Or is that
compose.
literally just multiplying the thing by a constant?
You mean is L2, does it mean L compose L?
Yeah,
Is
or does it mean like
Oh, no,
it's
no, no.
like
It
well, yeah. What is
uh
little L here?
okay, sorry for the confusing notation. The little L here, these are the components. These are the components.
Oh, these are the basis components
Yeah,
from the basis of V star.
yeah, yeah, correct.
Oh, okay. So
So
F1
L
is the okay. So
L1,
so F1, if you put in F1 on a vector that only has L1, then it maps L1 to one. I'm guessing.
yeah, yeah.
Okay. So you're just like
So they're
dynamic
just
scaling it by that thing,
yeah, components. The components
right?
of the dual of the components of the vector of a dual vector. Yeah.
Okay. Yeah. I
With
guess you really have to have them to be C, just some field.
Yeah, so this is not it's not L compose L. Sorry if that
Okay.
notation is
Yeah.
confusing. Um
So
um
it's just like you're just scaling the map, the
yeah,
F, right?
yeah, that's right. So
Okay.
you consider how each of the F's F is a Fi is a basis for V star, and
Okay.
then
Yeah. Yeah.
Fi will tell you how it acts on each of the basis vectors. So you're just scaling that.
Right. Okay.
This is assuming the case of finite dimensional. In the case of infinite dimensional vector space, then the dual space is actually is a bit more involved. Like dual of a dual is not the original vector space because it's some funny stuff with convergence and
Okay. Right.
yeah. So we just assume finite dimensional for simplicity.
Okay. Sure.
So this ln so this would if you write this right in terms of if you want to try to express that in terms of row and column vector, it kind of looks something like that. Ln and then you can consider as a dot product or something.
Okay.
So I guess there's a few ways to think about it. You can think of it as a row vector multiplying a column vector,
Hmm.
v1 to vn, or you can think of it as like a column vector l1 to ln as a vector, right? Dot product with v1 to vn. There's no
Okay.
correct way to,
I guess the row thingy, whatever.
yeah, I kind of,
Okay. Like the second line there, that makes like quite like. Let me see. Oh, oops, pen. How do I need to change to the moving tool? There we go. The pen tool. Yeah, I mean, I like
the second
I
one.
guess I like this way. Like I personally prefer this way. Like
Sure.
yeah, because this is like like oh yeah, but okay, I guess it's convenient notation. Yeah. Okay. Cool. Yeah.
Yeah, so I like the second one because it highlights the difference between if I consider the third one, right, the dot product one, it does if you look at this alone
Yeah.
notationally, it doesn't seem to
This one is also fine too. I think like this is a close contender for me.
this one, the second one.
Yeah.
Okay, so this is good and the two here are good. So the third,
This is just confusing. It's like
yeah, this is bad. This is bad.
oh
So I like this because it then now whenever we have a row of numbers, we can think of it as an element of we can think of L as being represented by a row vector. Um,
right.
so like in some sense, the vector space V is when put in components is represented by column vectors, and V star is represented by row vectors. And
Okay.
then that would probably lead us somewhere when we talk about this map M transpose to V star, transpose from V star to W star. So maybe we consider if you consider back to the original question, what does a matrix look like in components? A matrix M when it maps a vector V to W, um, it would
Right. Yeah, just like doing multiplying
component
each
wise,
one.
right?
Yeah.
Yeah. So
And
in
putting in.
basically
Okay.
we will map each of the we'll map each of the basis vectors EI
Okay.
into in to a resultant basis to a resultant vector in W. Okay, so I mean it looks like a matrix. So We have a
Yeah, I guess
matrix.
you just do that way, yeah, because
M is a
it
matrix.
works, yeah.
And we express V in terms of if we express V in terms of basis vectors, then we get the components of V in a column vector, and then M is this is M. And so basically each row over
Right.
here. Uh so when we do the multiplication, yeah, we get
Well, let's just consider like a 2 by 2 matrix for now for simplicity's sake, I
sure.
guess.
So
Yeah,
this
so
will equals to A, this will equals to A
this thing.
x1 plus B. Wait, my mouse is a bit funny. Plus B x2 C
Oh,
x1 plus
so like a bit of abusive notation here. So like if this is M, right, then it's kind of just
Mhm.
like, let's say like the component of M are like M1 and M2, right?
Yeah,
Then like you just do M1, and then this is V, right? It's M1
yeah,
V for the first row and then M2
yeah.
for the second row. Okay, yeah, it's a bit abusive, but okay, I
So
guess it's a nice way to think about it. Yeah.
yeah, I guess we can think of M. We can think of the rows of the matrix M as each one of them. We can think of each row as a dual vector.
Right.
Yeah.
Oh, okay, yeah. So that's why right. Okay,
Yeah.
that
So
kind of makes sense, yeah. Because like
yeah,
it does turn into scalar because M1V is a it turns into right, okay.
yeah. So with that, if each row is a dual vector, then yeah, let's see how that relates to the M transpose. So if we do transpose on a matrix, each row becomes a column, and each column becomes a row. So suppose we do transpose,
Okay.
then our matrix M, our row vectors becomes columns.
Yeah, so
So
it gets split on the side, right?
each dual vector becomes a column. Each dual vector becomes a vector kind of. Uh, okay.
Okay.
Um. Yeah. Okay. So so if we consider this M transpose as a map from how do you think of it as a map from V star to W star? Um. Okay. So let's if we consider the matrix M as a bunch of column vectors, right? Uh.
Okay, never
Then
mind. Just me I was just trying to think if it's like some group theory thing going on here. Yeah.
if we act it on a row vector, right, an element of let's say we act it on F over here,
Sure.
where F is an element of V star. If we act it such that the matrix M acts on the right of F, then 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 this will produce
So the right is we have the F doing the thing instead of like M. Because like we have like say this is like C1, C2, C3, right? This is like FC1, C2, FC3.
yeah but it'll be arranged in a row. It'll be arranged in a row. So we FC1, FC2, FC3, right?
Okay.
So it'll be arranged in a row like that.
Right.
We multiply
Yeah.
numbers out. And then remember row vectors, we can think of it as elements of a dual space.
Yeah.
Um and so question I guess is what dual space is this? And I guess we can kind of try to show that the dual space that this produces is dual to W. And okay, let's try to think about how that happens. Okay, so the picture so far to summarize, right? We know that column vectors are elements of vector spaces.
Uh-huh.
Um, row row vectors are elements of a dual space. Uh, Um, and then we know that matrices, right, which can be thought of as a bunch of row vectors, is a map from a vector space to a vector space.
Okay. Yeah.
And on the other hand, if we take the dual of this matrix, if we take the transpose of this matrix, all the
Okay.
vectors become column vectors, and this transpose matrix can be thought of as a map from V star to it maps the elements from V star to some dual space, to some row vector. So basically all that remains to show is that this thing over here, we want to show that is W
Speed
star.
star. Yeah. W star, sorry, yes.
Yeah. So uh okay, I guess that kind of makes sense, right? Oh, okay,
Yeah.
actually it completely makes sense because if you think about
Yeah,
um
I get what I like. It kind of, yeah, it does make sense what's going on here.
yeah,
Like the flipping kind of makes sense. Yeah.
yeah, because MV, if it equals to W, right? Then if MV equals to W, like each component of W over here, right? Each component of W is precisely
Yeah, yeah. So each one is just a dot product of each like row in
yeah,
a sense in the M,
yeah.
which
So,
is
so
nothing but the dual factors.
yeah, exactly. So I think okay, my pen is not. So each W over here, this black dot is this row dot.
Yeah, we can just use the abusive notation, right? We can have like, yeah, we can just use abusive notation. Hold on. Wait, let me do it this way. I think probably this makes somewhat more sense. So like pretending like this is the matrix and then this is,
Mm,
and then like the components of, and then this is V. What's the
mm.
M1? This is so abusive, but
Yeah. So
yeah, so something like that, I'm guessing.
yeah. So basically WI, the ith component of W is the matrix, the row of each matrix multiplied by the
Yeah, yeah,
vector. And so
yeah.
this is a complex number. This is a
Well,
element of
it doesn't
uh,
really have to be a complex number, right?
oh well, I mean the underlying field. Yeah.
I mean, as in like, could we? Well, I guess
Maybe yeah.
what
Sure.
about modules? Nah, that's for you. I don't even know enough about. I don't even know enough about modules to talk about modules. So never mind.
Yeah, neither do I. Okay, so if we think of the transpose matrix as a M transpose as acting on elements of V of V star, right?
Right.
Then from the right side, then that looks exactly like so the picture will look something like that where the now each row becomes a column,
Okay.
and then this is the F, which is basically
Okay.
an element of V star. So this is a row vector F1 order to F, and this one is an element of V star, and this produces, well, if the row here became a column here, and then the V F is just equals to the original vector but dual,
Okay.
then
Okay. This is confusing. What? Okay. So F is a map, but then
oh, okay, sorry, maybe this is bad, yeah.
this
Okay.
is, wait. What? I'm so confused.
Uh
One sec. Where's my? I probably have a linear algebra textbook sitting around somewhere. Let me have a look. Um.
okay, how about this? Given the vector V in the vector space V, right, of we can think of the components of V as a column vector, correct? These are numbers V1 to Vn.
Sure. Sure. Sure.
Then
Yeah.
we can think of an isomorphism between V and V star by simply taking these numbers and flipping it to become a row vector. So right now we are defining an isomorphism by considering the components and flipping it.
Okay. So vectors are just kind of just maps. Well, I mean, they're kind of just that. So if we, I'm trying to. Hold on one sec. Okay. Um. Okay, but like I mean, like okay, as in. Uh, Okay, what if okay, as in if this is like kind of concrete and draws too much on the real number, like the Rn analogy. So what if we just had like an arbitrary like vector space that we didn't know anything about? Like how would we, you know, turn into the dual space? Like I'm
Uh,
guessing, is it just depending on like the action like of like we have a V, right, from some V, and is it just depending on the action of like
mhm.
V star like equals to some C in in the field, right?
um, uh,
So I'm
wait,
not too sure how like this. works.
Okay.
This F is bad.
I'm trying to define, given an element of V, right? If we do not make a purposeful choice, it just stays in. If we do not, okay, given an element of V, the vector space V,
Yeah.
nothing in nature tells us that it's isomorphic. That there's some nothing in nature tells us that there's some corresponding vector V star
Okay.
that this V maps to, right?
Yeah.
Like it's a structure that we impose on the vector space.
Ooh. Okay. Now I'm kind of lost because like I don't as in if you of course like if you tilt it on the side it looks isomorphic, but like I mean in like a more abstract sense, how would it be? Like
Uh
isomorphic.
so I understand what I mean. So it's
Yeah.
like question, maybe one question we might have is, does this depend on the basis? Does it depend on basis, choice
Yeah.
of basis? And yes, it would in fact depend on a choice of the basis. Um, so like this is dependent on the basis in V, and this is dependent on the basis in V star. Um,
Oh, I think I get what you mean. So like if we pick a specific basis for V and V star, then they can be isomorphic. But if we change it like say to like some different basis, like say B1, and then this one is like we pick B1 star, right? They will probably be isomorphic like this. But then if we do like B2, it might not be B1
yeah,
star, right?
yeah, but actually we made the choice. We when we pick a basis in V, right?
Yeah.
We
Like
made a specific
also
choice of
simply
the
pick
basis
the basis in V star.
in V star by precisely choosing the
Okay. Okay. Yeah. Okay. Okay. That makes sense. Yes.
yeah,
Okay.
because
Cool. Yes.
nobody said that the basis in V star needs to satisfy this. This is something we impose by
Sure,
ourselves.
sure, sure. Yeah. Okay, okay. Then that makes sense. Yeah, yeah. Okay. Yeah. Okay. That's clear. That's clear. It's much
Great, great.
clearer.
So
Yes.
yeah, so
Mm.
maybe with this imposition, right? This imposition implies that there's a isomorphism because
Yeah. Yeah, okay. Yeah. I can see it
uh,
now. I can see it now. Yep.
so yeah, I guess this is the underlying step that we're doing.
Sure. Yep. Okay. Yeah.
So
Makes sense.
yeah, great. So when we choose a matrix, we choose a basis for V, and we have a matrix action on we have the matrix action on the column vector. If we transpose the matrix, we can think of the any element in V. Initially it's MV equals to W, right? We can think of the transpose action as M transpose, and then we take V star, right?
Okay.
We make V into a dual. This equals to, and this will give me, so this if we calculate if we calculate it out, right, it will look like your M1s is now are now uh your M1 and M2 and
Yeah.
M3
Yeah. Okay.
you wrote
Yeah.
over here is now becomes columns.
I guess you could just be M1 star. You could just call them M1
Uh, yeah, sure, M1 star.
like in the rules.
Yeah, yeah, that makes sense. Then your V star is now your
Confusion.
V star. Your V star is now V1, V2, V3, and so on.
Okay. Yeah. So this is V star.
So this is now a row vector.
Okay.
V1, M1 star, so on to Vm, Mn star.
Uh. So like V star. One star. V. Hold up. I thought we're like just multiplying like for like each row to the thing like likewise with
Mhm.
like okay how does this like right multiplication thing work, like okay like dropping the dual stuff, how does this work?
Okay, this works if V is a row vector and M is a matrix. So
You can't like if V is column then that doesn't make sense, right?
yeah, if V is a column, then that doesn't
Okay,
make sense indeed. Yeah.
so but if it's a row vector like doing M with the row vector doesn't make sense. Like,
Uh,
if V is a row vector, this doesn't make sense, right?
wait,
Do like thing like this, that doesn't make sense. I'm guessing.
the right one being a row vector.
Yeah. Like if that doesn't make sense, right?
Yeah, that doesn't make sense.
Oh, okay. So that's why. Okay, so left is the only way we can do this. I'm confused because I thought we had like
Yeah.
a right version. Okay, cool.
Oh, yeah. That the only sensible way to do it, if
Okay, yeah.
we consider V star over here, then the V star over here that we initially wanted to
Yeah. Okay.
answer, then this is the only sensible way I can think about doing it.
So we have MV, then we get V star transpose.
Yeah.
Busy. Okay, bye. Have
Yeah,
fun.
yeah.
Yeah.
Yeah,
Yeah.
basically what you wrote over here. M
Okay,
V
yeah.
star and M
So
transpose.
M, because I said M was like continuing to use my super abusive notation. So if like M transpose is literally just M1 start, 2 start.
Oh no, don't arrange it as the S stars, don't arrange it as a column. Because each of the M1 over here, each MI is a row vector, right? So MI
Yeah. So then it
star
should be just M1
the column vector.
start to.
Yeah, that's right, that's right.
Okay, yeah.
So this is
Okay,
M
that was
transpose.
that was too abusive. Yeah. Okay, yeah.
Yeah,
So
so this is M transpose.
okay, so now V star M transpose equals to
Mm-hmm.
V. Oh, okay, now see now okay that makes sense, right? Because
Right?
like
Yeah.
multiplying these two like this thing.
Yeah,
Yeah.
exactly.
Okay, yeah, that makes more sense now. Then you have your result is just like V start M1 start V2 start M2
Yeah.
dot.
Yeah, that's right. That's right.
But not really like V like the vector multiplied inside by each by itself, not V1 or whatever. Yeah. So like it
Mm-hmm.
would be V1, V2, V3.
So each one of these is a complex number, right? Each
Yeah.
one of this is a complex number. Oh, sorry, F if you wanna if
Yeah,
you
yeah, sure, yeah. So, but like
yeah.
as in not it's not if it's V1 and V2, V3, but if we use but if it's V1, V2, V3, it's just each one this is like the row the column vectors. Yeah.
Oh, actually, I don't think you should use it as a V1 V. It's just V star.
Yeah, it's just V. I mean, it's just V star. Yeah, but it's like if we are using V1 dot, then we'll be like that. Like it'll be like the
Mm-mm.
columns. Yeah.
Yeah. So at the end of the day, um, the M transpose acting on a element of the dual,
Okay.
this is a row vector,
Yeah.
and
Okay, that makes a lot more sense now. Yeah.
this row vector
Yeah.
is an element of
Mm.
is an element of W star.
Sure. Yeah.
Yeah, because if you transpose it back, then you just get back W.
Okay.
So at the end of the day, I guess to answer the question of what this means,
Okay. Yeah, that makes more sense now, right? That makes more sense. So like, okay,
yeah.
I still don't get the motivation behind the transpose. So like, what's the point? I still like what's the point of it?
Okay, the transpose, I don't know at the moment exactly what's the point of defining a transpose, but if you want, the transpose is used in orthogonal transformations. So, uh, you know the definition of orthogonal transformation.
No, I don't know. Yeah.
Let's see. Okay, let's see. It says that orthogonal transformation from
Linear transformation and real inner product space. I have no idea what
preserves the inner
inner
product.
product is dot product. I'm guessing.
Yeah, basically it preserves dot product. So if I draw an analogy, you know the vectors in 3D space, right? We
Yeah.
have we have a definition of a dot product, which kind of gives you the angle between them.
Yeah. Yeah.
So if you
Sure.
consider a linear transformation, such that is this one maps to a new vector like this, what it means to preserve the inner product means that the angle between them doesn't change.
Sure. Yeah.
So in some sense, it's a linear transformation that preserves angles. Um, and that corresponds to like a rotation of the basis. It's basically a rotation of the basis.
Okay, that somewhat makes sense. I'm probably gonna have to look into it more, but
Yeah, sure.
sure. Yeah.
So basically, if we give the original vector space V, vector space V is just a vector space, but if
Right.
we imbue it with some additional structure of the inner product, then one can kind of define angles between vectors, and the imposition that the orthogonal transformation leaves this inner product invariant means that the orthogonal transformation respects angles. It doesn't change angles between
Right.
vectors.
Right.
And yeah. So there's an equivalent definition in terms of the orthogonal matrix is defined as so orthogonal matrix is defined as a Q transpose and Q is
Okay.
the identity And does that make sense? Not really at the moment, because if we think of it as V, if Q transpose is a map from
Okay.
V star to V star, then this doesn't really uh, make a lot of sense, right?
Normal. What is this normality? Like it's the same as the group theory normality, right?
Oh, no, no, no. This
As in, it
orthonormal.
says, no, as in below it says it's normal. Q star Q equals Q star. What the heck is a conjugate transpose now?
Conjugate transpose is um is where you not only transpose, but you take the complex conjugate. It
Okay.
arises it arises when you take the when your inner product is when your inner product is not only, okay, currently the three-dimensional vector space, the inner product, the dot product is using real numbers, right?
Okay. Yeah.
But if you get a complex vector space,
Okay.
complex V, where your underlying field is a complex number,
Sure, yeah.
then then uh then your inner product would need to your inner product would need to between V and W, right?
Right.
This, if you take the if you swap the two positions around, okay, so maybe I give a bit of background. So
Yeah.
in a inner product space, usually you say that the inner product must be symmetric, right?
Yeah. Okay.
So usually we say that inner product between
Yeah.
V and W must equals to W and V.
Yeah. 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 That
And
makes sense.
this is when the underlying field is the real numbers.
Mhm.
Um, so inner product gives you an element of real number. When
Right.
you swap it around, it also gives you an element of real number.
The same
We
real
say that
number.
they're related by, they swap it around, doesn't matter. But if your underlying field is a complex number like this, then you swap them around, right?
So the inner
They
product
are
is related. Yeah.
they're invariant, but up to conjugate. So like when you swap them around, you must pick up a
Oh, okay. Right.
conjugate. Yeah.
Okay.
And the reason for this is, if you do not, then okay, why do you want to define it this way? Um, Hermitian Hermitian inner product.
This feels really weirdly unmotivated for some reason, but
There is a good motivation, but
I mean, I'm sure there is. I just, lol. I guess.
Hermitian adjoint. Let me try to think about why we want to do that. I know we always use it a lot. We use it to the point that it becomes a normal thing to define, but
Yeah. Okay. I guess you use it in physics. I mean, like, I'm struggling. Okay, I'm struggling to think of if there's like some application in like, um, I don't know, like abstract algebra that we use it for. Um, hmm. One second. I wonder if this book covers it. Okay, the index.
I
Like
like
that.
to think,
This is a lot of shit. Okay.
yeah, question then, I guess, why do we want to define inner product this way?
Uh, let me see. Let me see. Okay.
Oh, but there are other ways to define product. There's like sesquilinear product and things like that.
Okay, wait, one second. Let me have a look at page 521. What is theorem 28.3? Wow, okay, this makes no sense. Why is it after freaking Galois theory? What the shit? Okay, sure.
Galois by Galois. Uh, a bar over the thing representing a scalar denotes the conjugate transpose. I'm looking at the definition of an inner product space right now. This is called conjugate symmetry. Uh,
I mean, I guess conjugate symmetry still preserves it on the real numbers because if you like, because like if you apply conjugation, real numbers is still the same. Yeah.
so conjugate symmetry implies that when you have a vector and it conjugate and the inner product with itself is always a real number.
The inner product of this self is a real.
I know why now. Okay, so something when we define an inner product space, we're defining we are defining an angle, right, between vectors. We define kind of an angle between vectors, but at the same time, we're also defining a notion of length. Right? In fact, actually, inner product is more about a notion of
Mm.
like when we have a when we basically want V when we inner product with itself, we're on the way to we want this to be always positive, uh, always greater than equals to zero.
Right, right.
Uh, where equality is only occurs when V is equals to the zero vector, right?
Okay.
But this notion of inequality, right, it only is only defined on real numbers.
Yeah, because we can't order
Yeah.
we can't really order complex. Yeah, that makes sense.
Yeah, it's only defined on real numbers. So that would mean that when we take V of itself, we want it to be a real number, right?
Okay, yeah.
And that's the motivation for the imposition of conjugate symmetry. Because conjugate symmetry would
So,
imply that,
like I'm guessing the inner product is something we want to have like ordering on.
yeah, or rather we just want the notion of length, which is defined as inner product with itself, to
Is
have
this,
a real
I feel
number.
like this is some like some I don't know if this is some measure theory thing or like some metric space thing. Because like feels like like you want length. So like
We want length.
maybe it's, I don't know, maybe some metric space thing.
Hmm.
It might
I
be right.
I
If
haven't
it does feel like some metric, it does like as in, it does feel like some kind of metric space thing.
See, you might be right because
Yeah. Because like if you want like the fact that you want some length, it just reminds me of like we want to put like it's like putting a metric or something. Yeah.
yeah, I would think so because if you because it's Hilbert space we use in physics quite a lot, which
Sure. Yeah. I
I
have no
guess
idea
is
what spaces. Can you introduce
uh,
me to what that is?
it's an infinite dimensional the infinite dimensional vector space. Okay, sorry, that's inaccurate. A Hilbert space, okay, but in physics we 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 use Hilbert space quite a lot to at quantum state is defined as an element of a Hilbert space. That's the
Okay.
thing. Yeah. So often when we construct a theory, we often say we want to build a Hilbert space, meaning that basically we want to find all possible states of the theory.
Right.
Yeah. So like the Hilbert space is something that we want to quantum states are defined as elements of Hilbert space. So we usually want to map out, like we want to construct the Hilbert space, um, and understand how the vectors inside work.
Sure. Yeah.
Yeah. And then like time evolution will be an evolution will be seen as a unitary transformation on the Hilbert space. So like quantum
That made
states,
no sense because I don't know any physics.
okay, like quantum states, they change over time also, just like how like if you have the mass and velocity, sorry, if you have the velocity of a
Yeah.
object and the position, right? The velocity
Yeah, I
and
get
the
that they're
position
probably just some
changes over
time
time.
function, right?
Yeah, some time dependent function. So the Hilbert space is a map from some time t to the elements in the Hilbert space.
Okay.
There's some notion of a curve in the Hilbert space, and
Yeah.
yeah,
Yeah.
that's how time evolution comes about. And if we want to, the notion of unitary also comes in when, uh, like, uh,
Product space which induces incomplete metric is the space of continuous complex valued functions on the interval AB, and the product is
yeah.
yeah, okay, it's not complete. Yeah.
So
So the
yeah,
sequence
maybe you're right. Maybe you're right. The definition of the reason why we want to be real
is
and hence
motivated
have
by
a
like
notion of
trying to put a
length
metric on it.
is probably motivated by that. Yeah. Although I can't really put a pin on it, but oh,
Huh.
you want to define a norm of vector? Yeah, that's
Ah,
pretty
and yeah, okay, that is definitely a metric.
okay. Yeah. So
Yeah,
if
okay, yeah, yeah, they were trying to turn into metric space. See,
yeah.
triangle equality.
Right. So you
Yeah,
want to turn your metric space. So you want to define a norm on it, and you need all these properties, and hence we want only the real numbers have such a nice property, right?
yeah,
Although I'm wondering, does that imply what we try to define like norm of a vector as
yeah,
just like I don't know, we can define something really stupid like the 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 length of the length of this,
sure, yeah.
right? Meaning the absolute value of it. Would that work as
I
a
guess okay, but doesn't this depend on like the metric, right? Like if you have like the usual, like this feels fine if you have like the usual Euclidean metric, right, with D, and like I think you could just do like because the length of that is literally just like you take like it's just D of V1 like VV
hmm,
V1 like well it's not really like V with like rotating. Wait, hold on. How would that work? Okay. Let me quickly draw a 3D grid. One annoying quip is that they don't support the double click gesture on. So on iPads, like if you have the pencil, it double clicks.
Yeah.
But like it doesn't support. This website doesn't support it yet.
Wait, I'm pretty sure they did support it at some point in time. I'm not sure what changed.
It's gone now though. Yeah. So
Maybe I should. I know the owners of this.
yeah, you can maybe ask them what happened.
Yeah.
I'm very sure this is not how IJK works, but that's fine. Okay. So if you have one here, then you do it itself and take the square root. What even is length in RT? Length, what the frick is length in RT? It's just the cube root of like the x squared plus y squared plus z squared, sorry. Oh, no, it's the square root, it's not the cube root. So it's, this is confusing. This is interesting. What the heck? Hold on. One of these books have got to have something.
Like, oh, you're wondering why is it a square root and not a cube root?
One sec. One of these books has got to have something. It feels motivated, but I can't quite put my finger on it. It definitely feels. Yeah. Hold on. It feels motivated. Okay. No, I don't see anything here. That's interesting though. Oh, I lost my bookmark. Wasted like 1 hour at the freaking this university like event here. I wanted to get free food from them, but it turns out they didn't have free food. It's so sad. So yeah, but anyway, I used it as a bookmark, I guess. Cool. It's in Vancouver. It's where Electro Boom lives in, actually, I think. Does he live there? Oh, yeah, Electro Boom lives in Vancouver.
I see.
And Linus Tech Tips also.
Cool. Oh yeah, recently Linus Tech Tips, he managed to recover his stuff. That's good for him.
What stuff?
Like his videos.
Oh, I thought he never lost them. What the heck? Oh, you mean the hack? Yeah.
Yeah, he got hacked.
Google. Okay, this is because Google has a really scummy policy, right? When you click delete, it doesn't actually get deleted. Yeah, it just gets stored. Like Google, Google is basically spyware. Like, well, I mean, yeah.
Once it's uploaded,
it's like as an event, and like I'm pretty sure when I deleted all my, because I deleted all my privacy for a bit, but yeah, okay.
This meeting is being recorded.
Yeah, I feel like, yeah, I mean, where did group theory even come from anyway? Like was it like, I don't know, where did group theory come from? Was it from like studying like vector spaces, or was it just from like, I don't know?
No, it came from studying symmetry. Group theory came from studying
symmetry. It developed separately from vector spaces.
I would think so, yeah.
That's interesting.
The thing is that I realized that what made it click for me was the notion of function space, because functions are, I mean, anybody who's
that's just a symmetric. I mean, that makes sense, right? Because you have like symmetric groups and shit.
Yeah, like the notion that made it click for me was that you have a function space, derivatives are linear operations on functions. Then notion of basis, you can think of a function as when decomposed in basis, you can choose the real basis, right? Where it's just the function evaluated at every point in space.
Okay, yeah.
The components are the function evaluated at every point in space.
Yep.
And you can think of functions as when decomposed in another basis, like for example, Fourier basis. That made it really click for me. That made me realize that linear algebra is more than just matrices and like numbers.
Yeah, I think again, once again, it seems to be a pedagogical problem where like you introduce linear algebra, like, look, here's a matrix, here's a vector, memorize how to multiply them, instead of like, oh, here's what we're doing. Because I like the basis transformation one, because it also like, it reminds me a lot of like the way in topology, like you could have like multiple bases for like the same thing, for like the same topology. Yeah. like it makes a lot of sense, right? But then there's like a lot of things that are still preserved, like if you have the same topology but like different bases, and then like like, so basically you can like transform one open set into another.
Yeah.
It vaguely reminds you of that. I mean, I'm pretty sure the reason it vaguely reminds you of that is because like this kind of thing motivated them to study like topology and whatnot.
Mm.
Yeah, but yeah, that's interesting. Why is everything just a pedagogical problem? Like, I don't even get it. Everything just is a pedagogical problem. Every bad experience I've had with math is a pedagogical problem and not actually math. Like,
Well, I think pedagogy plays a big role in shaping one's opinion on a subject.
yeah, that like it's so bad because like if you like I absolutely dislike the way that like school math is taught. Like, but like well, I read textbooks for fun because the textbook is actually written well. It's so shocking, right? Like, how is it that a university level textbook is written in a way that is actually fun?
Mm.
The author is like so like chill, and playful, and like the examples are good, and like it's like you actually understand it. VS like freaking schools like, oh, here's calculus. Oh my god, like I don't even get me started on how the way the calculus is taught.
Yeah.
It's so bad. It's just bad. Pedagogy is bad. Like I feel like at this point, right, it should be mandatory, right, to take a course in math pedagogy before you're allowed to teach math. In fact, for any subject, it should be mandatory to take a course in pedagogy before you can teach it.
Well, that's the whole point of okay, let's not get too political, I guess, because you're not gonna have to pause the recording again. But I feel like if
I mean, as I'm not really talking about politics here because I'm not sure like what the framework is of this. I'm just like throughout.
I'm not going to push it towards the political end.
Yeah, as in we're not here to discuss the political stuff yet.
I feel like if given the right introduction to like Chinese literature, I could actually be interested in it as well.
I feel like most of my I feel like most of like my so-called hate for like certain subjects it's just because I wasn't like it was not taught to me properly.
Yeah.
So I didn't like it.
I would think so too.
Yeah, like for example, like freaking like literature, right? I did poorly in it because I actually hated it because it just felt so weird, unmotivated. Like and like I think same with like I feel maybe that's why I hate like probability and stats because it's just like here's this thing, here's some formulas, you calculate it. It just feels unmotivated. Yeah. It makes me wonder like how do they think this is like a good mathematics curriculum? Because it's not like it's not like learning to compute these formulas. Like as an arguably, yeah, sure, like all this I'm pretty sure topology is like not much uses in my job, but like arguably it's like, it's more helpful to my brain because it teaches you how to think. Like I think yeah. So like why don't they just like, teach all this stuff? Like sure you probably aren't going to use it and like I don't know, maybe I don't think it's actually that hard for like most people to learn, but maybe I'm just wrong. Like yeah, I feel like just all this like randomized computations is just not the right way to teach it, right? I don't know.
Yeah.
Like surely it can't be that hard, right? I mean, like if you introduce group theory in like high school, a lot of people will probably find math really fun and interesting. Or like heck, like maybe not analysis. Analysis is quite a pain in the butt.
Yeah, analysis is a pain.
Oh god, it's so painful. I spent 3 hours yesterday on 3 questions at work. I spent 3 hours. It was so painful. Analysis is actually really hard. I hate it. Well, I don't hate it. Okay, as in when I say I hate it, it's more like I hate it, but I'm still good. Like as in like a loving way, like so frustrating, but you still do it anyway because you find it interesting. Yeah, that's what I mean. Yeah. Yeah, but like I don't get like this weird like the way that they do math pedagogy nowadays. It's like I don't know. It's not just like a Singapore issue. I feel it's like kind of like issue of like a lot of places in the world actually. Like the way that they teach math and like unmotivated, like calculate these things. Yeah, I don't know.
Yeah. All right. I think I should probably go. It was been a nice chat. Yeah.
Okay. Cool.
Thanks for helping me. It's through conversations like this that one starts to think about the motivation for certain things, and I guess it helps deepen.
I guess I don't know. I guess I mean as in I'm sure there's like a lot of applications in physics, so like you probably aren't too short of motivations there, like as in because it's like when you look at this stuff in like math is like like where will we use this in other bits of math, right? Because like as in As in, yeah, as in like you don't really need to like apply in the real world, but as in like at least like some useful applications and other bits of math. Otherwise, the definition is just like random. Oh, by the way, speaking of math, right? Have you? I learned about this thing called a fuzzy set recently.
Oh,
Right?
I
Yeah, you should
saw
do
it
that.
before, but
It was kind of funny. I thought it was a joke. I was on Discord. Like, I was in the mathematics Discord, and like one of the guys that was talking to me about it, I was like, "What the heck is the point of this? Like, I don't get what's the point of this." Mm.
what does it promise to solve?
Okay, apparently one of the main interesting things is the fuzzy logic there. Like you see, yeah. So like how like how how like normally in our current like logic, right? Like things are either
Say
true or
yes or no, yeah.
yeah, but in fuzzy logic, you have things that are like 0.3 true or like half true.
Oh,
Like,
long.
yeah. But as in the intuition behind half true doesn't really make sense, right? Like,
Well, I mean, if SET has different degrees of membership, then that kind of seems to make sense. Like saying whether something equals to uh equals to something that's in a set or not, then it could carry forward.
okay, I guess that could make sense. Like it kind of defines like a notion of distance from thing in the set.
Yeah.
For example, like for example, like okay, like for example, like a very trivial example, right? Like let's say like half is let's say like the number 1/2 has like half a membership in the set. That means like that's probably that means like maybe intuitively you could think of it as like there's a thing in there that like half is like a distance of like half away from the thing that's fully in the set, I guess. I don't know.
Like what is this used for?
Yeah, I had no idea. Like I'm like as in it says this fuzzy logic is interesting, but like
Fuzzy
what is
logic, I see.
like I don't know.
Applications? Oh,
Hmm.
AI, medical decision making.
The medical decision making just sounds like a really cursed thing to
Yeah, dude.
use it on. Like,
Imagine,
decided
imagine.
there's only 0.1 treatable, so we're not gonna treat.
I'd rather my doctor tell me that you have a probability of having cancer than saying like, where we use we use a fuzzy ambiguous logic to determine that yes, you have cancer.
You have cancer. You have a 0.1 cancer. You will die. We have determined that you will die in 50 years, but that is but in the set of years that you probably die in, we've determined that 50 has a membership of 0.3. You can't even interpret it. Oh, I spent a lot of time at work reading on relational databases, and it's actually really interesting. Like, it's apparently based on. It's not like relational means like the database table, like it's literally defining a relation, right? Like if it's in like the table, so like the way that like the reason it's called relational database is because like if you have the table itself is a relation on the data, right? Like so for example, if you have like a users table, right? If A and B are like so you think of the users table as the relation and like but there's also a set in a sense. So if you have A and B are members of users, then A tilde B, right? Right. Tilde is the equivalence relation denoting them being users. And then each column is literally a tuple, which is why SQL Alchemy gives you back those tuples, right? Because it's literally taken right from the relational database, which is like they are literally like just the Cartesian product of the columns, right? But the columns are the sets of things, and you just take the Cartesian product on them. Yeah.
I see.
So
this is interesting. It's an open question to give support for church thesis for fuzzy mathematics.
the proposition.
The notion of recursive enumerability for fuzzy subsets is an adequate one.
Wait, what is fuzzy mathematics? Can you click on that?
What is fuzzy mathematics?
Yeah, can you click on that? Thanks. Plug in my.
Well, I guess it's just what you described.
Technical for readers to understand. No worries, we can still read it. Okay, usually a falsification mathematical concepts determine generalization in the context of characteristic functions, the member functions that A and B be two fuzzy subsets of X. The intersection A intersect B and union A union B defines as follows. A intersect B on X is the minimum of A of X and B of X. Oh, so A is probably just measuring the membership of X. Yeah. A union B is max, and then instead of min and max, one can use T norm and min AB can okay. Poisson generalization of principle of falsification of algebraic closure operation. Wait. What?
I'm going to read the recursive part because
That's
okay,
interesting.
the recursion theory is interesting.
Recursive enumerability of fuzzy subsets is an adequate one.
But this feels very
This
I
is
still don't really
this is just feels like, hey, we decided to invent a new field, logic.
yeah.
Yeah, like I don't know, like is it like, are they trying to solve something, or like are they trying to like fix like I don't know, like
Yeah,
change
what
foundations of math from ZFC?
what are they trying to fix? That's the
Yeah, I have
question.
no idea what they're trying to fix either.
At least type theory has application of being used in proof assistant, but this
it's
seems like
actually
mostly a
can
fun thing to
category theory be used as like a foundation instead of like ZFC?
uh okay, like yes, because ZFC set theory doesn't category theory you can kind of like think of as a bigger than set theory because things like infinity categories, they're hard to describe in a set theoretic language.
Right.
Yeah, so I would say category theory is an extension of it's definitely more powerful than ZFC.
So
So
right, so we can theoretically could just like rebase
yeah,
mathematics on category theory.
yeah. In fact, I do think that the direction that they're going towards is to develop math based on category theory. Like in future, we could be probably like ZFC might be quite an arcane theory. Like no, I'm being real. Like right now, we think about it, we don't really learn the modern interpretation of what's the topic like maybe metric spaces. I'm
Yeah.
not sure if historically metric spaces developed first or um or topology developed first, but like we don't learn metric spaces as like we understand metric spaces as a specific case of general topologies, right? Open set and stuff.
When was topology developed anyway? I feel like topology is developed to generalize metric spaces.
Yeah.
Yeah, let
So
me.
like in the same way, I feel that I would think that in future we won't really we'll be learning ZFC as a specific case of type theory or
Right.
category theory. That's
Hmm.
my
So you can,
opinion.
so maybe it actually like it falls out of category theory or type theory.
Yeah.
But like I wonder if category theory is like more elementary in a sense than ZFC. Like
I mean,
I don't know. Like I mean it's definitely not as accessible as set theory. Like if you think about it, because set theory is like,
that's true.
yeah, set theory is quite accessible, right? Like category theory is like a lot less accessible because like in order to learn category theory, you kind of need to know abstract algebra first, and to learn that you kind of need to use set theory. So like to redefine everything, and then I don't know, it just doesn't feel as elementary to me as like set theory. Like
Right.
isn't simpler
That's
better,
true.
right? Like
That's kind of true, I guess.
yeah, like sets just feel like quite simple things. On the other hand, like yeah, there are like the weird problems, right? Like yeah, like I've actually seen a few problems that someone posted in the math Discord. There was like real like exercise problems that had like where they got affected by the continuum hypothesis, which is like
Oh.
yeah, it's no, it's like as in they were just thinking like because you do an exercise like okay, I wonder what if I change this thing, and then it turns out if you change that thing, you get screwed by the CH, and then you can't do it anymore. Yeah. So just like I mean, you can do it by assuming it's true, but then yeah, so it's just I know it's yeah. I mean, I guess it is an interesting question, right? Because like how like if it's less elementary, then how can it be a foundation? Because now like until like so like the way that you learn the thing vs like the way that the mathematics is built up in the sense is like kind of on its head. Yeah, but I mean yeah, actually it's a bit of a weird pedagogical thing also, right? Because like you even though calculus was built on the foundations of analysis, analysis is really like analysis forms like foundation calculus, but then we discovered calculus before analysis. What's this? Oh, is this the Emily Real book?
Yeah, I'm going to I wanted to start reading it.
Oh, you wanna do it together? I kind of want to start category. I kind of want to learn category theory for some reason.
Sure, we can just browse through it, I guess.
Yeah, we can look through it. Let me go download it. Oh, this looks like a quite good textbook actually. Category.
But I'm not sure how we can give it a try because
Oh, it's just
really-
she just posted for free on her website. Nice.
oh wow, that's kind.
That's math. This is the official link.
The
so-
way I read it,
Please look. This is her official math department link.
I see.
Yeah. So she just posted for free. Nice. Okay.
No.
Let's have a look. Yeah. So. Okay. Yeah. I thought this was like some random textbook that you can give to like layman, but nope.
Because it requires context, right? And I feel that the context is important because
Yeah.
if not, you just feel like you're self-studying.
Yeah. Like just
something.
random shit. Yeah.
Yeah.
Yeah. Yeah. No, putting examples are good. Oh, okay. This looks good. She has a lot of examples. Wow. Okay. Yeah. This is wait, hold on. How much prerequisites you need? In principle, one could study category theory immediately after learning the basic set theory and logic, as no other prerequisites are strictly required. But without some level of mathematical maturity, it will be difficult to see what the point of it all is. We hope that the majority of examples are comprehensible and outline. But if it's not the case, it's not worth stressing over. Let's see what the examples are. Let me have a look. Oh, nice. Thank people from the NCAP lab. Lol.
Hmm.
And oh wow, these are like the math Twitter users.
I see.
Interesting. Yeah, like like a lot of look at this. I would like to acknowledge that these are like some of the math Twitter users. Let's have a look. Group extension. Okay, nice. It immediately starts with a fucking group extension. What a freak. Okay. I mean, I guess you need it. Okay, let's see. Category consists of a collection of objects and morphisms. Okay, this. Yeah, I guess. Oh, okay. This is yeah. Okay, yeah. I guess the examples do. It does pay to like have learned some of these things for the examples help. Group define a category. Oh, this actually looks like quite a decent book. Yeah, this looks like quite a good book. Yeah. Okay. Yeah. This looks quite good. This looks like quite a good book. Yeah. Interesting. There's actually I think there's also like a very OG book. Like there's an original category theory book. I think what's it called? Yeah. This looks quite good though. Yeah. This looks quite good. Yeah. Could do
Oh
it.
man, but I feel like okay, I can try to read it. I guess.
I mean, I get yeah, some of these examples are a bit, high up there.
Yeah.
I guess okay, as in okay, I get the topology examples. Oh, but I know why the examples are so like that, because like category theory came from AlcTop. So like half I bet you uses a shit of AlcTop algebraic topology examples. Group theory, group, ordinal. Yeah, I have no idea what an ordinal is. I know some ZFC thing. Set, category. Okay. And isomorphism we call automorphism. Sure, yeah. Huh. How can we use bijections though? Isn't that based on the set theoretic formulation? Yeah, how can we just use bijections like that? Huh. Top the group point. Oh, that's the homology thing. Yeah. Wait, hold on. Scroll back to the set to group thing. I want to see that. Yeah, F functor set to group that sends a set X to the free group on X. This is the group whose elements are. This one's interesting because I apparently learned out like a month ago that every set can be given a group structure. I think this might be it.
By the free group, yeah, that's right.
So like, there's no set of all groups because that's not a set. Yeah.
Mm.
Okay, so this functor F set group that sends a set X to the free group on X. This is the group whose elements are finite words, whose letters are elements X and X, or their formal inverses, modular and equivalence relation that equates the words X inverse. What would I look for?
Basically, things like X, Y. Wait, I'm not sure if I can draw on this. Like things like X, Y. If you have two elements of a group,
Wait, can you not draw?
oh,
Okay,
I don't think I can draw.
there's a highlighter.
Yeah.
We could just use you can just use the board, I guess. Or like the whiteboard thing. Is that a whiteboard thing?
Basically things like for the free group, if there's a single element,
Yeah.
then the free group is going to be X squared, X
Yeah, I
cubed,
know about the free group. I mean,
Yeah.
like, as in, what do they mean
X1.
by like that? The X inverse equivalence relation. I can't quite visualize
Okay.
like how we define
So
such.
sure. So if you have X and Y, let's say the generators are X and Y, right? Basically all the set elements become generators. So
Okay.
you have X, Y, you have 1, you have X, you have Y, you have XY, you have
X
Uh,
N Y N X
Y, X, and
Y
so
or like
on.
yeah, I get that. Yeah.
X, Y, X is still is different from
Yeah, I know.
X
Yeah,
and Y
I know that. Yeah.
because they do not
I
connect.
get what a free group is. Yeah.
But at the same time, you do not, if you have X, for example, X inverse
Mhm.
Y, right? This is just equals to Y.
Okay. Yeah. That makes sense. Yeah, because it should go to the identity.
Yeah. So that's just all that they're saying. They are saying all their formal words, right? Formal
So
words in their inverses.
X inverse should be
Is so this is equals to 1, and
right.
this is equals to 1. Basically, cancelled out with each other.
Yes, we just define. I mean, I'm trying to think of what such an equivalence relation would look like.
Okay, so you can think of it as a tree. This is the picture.
That's where all these pretty diagrams come from.
Yeah, so like think of A and B as different directions.
Okay,
Then if you proceed in one direction, let's say proceed in X, right?
and then you
And then
go.
immediately go in X inverse, then you get back to the original position.
Okay. So
Yeah, but if you go X
Okay.
and then you go Y and
X.
then you go X inverse, that's different.
Okay. Oh, okay. Okay, that's how you interpret those diagrams.
Yeah.
Right.
Yeah. So
I
it's
mean,
a nice picture.
freaking! I swear, I swear, I should have just like looked at these things for like a few more seconds, then it'll make more sense.
Yeah. So
Math moment.
so that's the free group.
Yeah. Okay. So, what's a word here? The word I
Word?
just.
Oh, word is just a formal concatenation.
Oh, I
basically.
can just concat those elements,
Yeah.
right? Okay. Okay. Oh, so that's how you assign everything in group structure. Yeah. Then the free group because you have a identity. I mean,
Yeah.
it's kind of. It feels like a cheaty group, because like, oh, we invented this thing specifically to be a group, and look, it's a group.
Yeah.
So,
Basically, you basically defined it to be a group. And
yeah,
then
it's
you say, oh, it's a group.
Right. Yeah.
But the free group is a universal property, meaning that
Oh, does it?
like the free group is basically it's an enveloping group. So like okay, how do I put this? So you have a free group, right, that is generated by basically freely generated, right? It's
Yeah.
There's all the possible formal words.
Yeah.
Then at the same time you have, let's say, the cyclic group, right? For example, cyclic group where you have it's generated by x to the n. It's generated by x, just that you have to
Angle
remember
brackets
that x
X
to the
will
n is
do
a
it.
1, right?
No, just angle brackets X is probably more familiar, I think. Yeah.
Oh no, but this relation is important because it concatenates.
No, that's forces to be finite. I mean.
Yeah. So finite cyclic group of, let's say, this is z usually zn, right?
Yeah, that's just Zn, yes.
Yeah, but then the free group is z infinity basically, right?
That's just Z.
They're just generated by z, or just z.
Generated by one, yeah. Like it's literally just one.
With no, yeah, sure. With no
That would be a subgroup of the free group of like XY.
Yeah, that's right. So Zn is a subgroup.
But then there's also a subgroup of like XYZ and then so on, so on.
Yeah. So subgroup of Z. But at the same time, if let's say you have Z2n, right? Z is a subgroup of Z2n also. Zn is a subgroup of Z2n.
Isn't okay, yeah.
And
Right.
which is subgroup of Z like 4n. And
Sure.
there's basically a whole, you can think of it as like a whole
A
tree
chain of groups, yeah.
a chain of
Like a sequence of
above it there's Z2n, then there's Z3n.
I've seen this notation used for like sub rings also. Yeah.
And so yeah. So you can think of it as a whole hierarchy. And basically
Right.
the free
And then
group is
basically extending the Zn thing.
yeah, all the extensions out of all the extensions, right? It
Yeah.
basically terminates here. It ends here,
Okay.
where it's Z infinity, meaning that
Everything is just a subgroup of this.
yeah, like this is the mother of all groups kind of. And
Yeah.
how one can think about it is that this actually the termination over here is kind of, I'm not sure whether there's something to do with the final object of a category, but you can think there's a diagram called universal
Mhm.
universality, such
Is
that
this
basically
the universal property of like
yeah
of those subspaces of topology?
yeah
Some
exactly.
right?
Yeah, it's the
Okay.
same notion. So basically Zn, if you have any groups have homomorphisms, right? Any homomorphism from Zn to some other group G, right?
Okay.
Then there exists a unique homomorphism from Z to that one that respects this diagram.
Yeah.
So that's kind of the notion to encapsulate
And
the idea that
the Z to Zn is just the canonical projection, right?
yeah
Just pi. Yeah.
projection
Yeah, it's usually just called pi, I think. Yeah. So just,
that this basically comes from the relation that x to the n is equal to 1, this projection. Yeah.
sure. Or like n dot x.
Polynomial.
It's a Zn. Yeah.
So that's also another thing that the free
Oh, that's
group
interesting. That is interesting.
mm,
Yeah. So that's how you give the set group structure by just like assigning the free group on the thing.
yeah. So in some sense you give it the free group structure, right? Then after that you can get any group. If this set is a set of generators, then you can get any group from the free group modulo some relations.
Right. So
Yeah.
modular is like just like quotienting by the
Yeah.
representation.
Actually, in hindsight, on second thought, that is the reason why generators are powerful, because of this property, right?
Generators are sorry, what?
Like maybe we can ask a question, can any group G be,
Mhm.
be can any finite group, right, finite group
Yeah.
G be written in generator form in the
Like
generator?
So can you or like this is like group representations, I'm guessing.
Yeah. Can group G be represented as some generators?
That's an
And
interesting question.
and the answer is yes, because
Hmm.
we can just take the free group
Okay.
of all elements, right? Of
Right.
all, we think of G as a set, right? We
And
forget,
then you find the equivalent, and then you define the equivalence relation.
yeah. So in some sense, all the elements in G, right, are just some complex relation between them, decomposed to a certain way. But if we just take all the elements of G and we forget G is a group, we forget
Okay.
all the group structure. So now G is a set of a lot of
Yeah.
lone elements, right?
Forgetful
And then we
function.
Yeah, exactly. Forgetful functor or something. And then
Okay.
now we take the free group on this.
Yeah.
Then we can get a huge group, very, very huge.
Yeah.
But if then impose all those relations again, then we're gonna get back the group G. So yes, in some sense, that does
Oh, that's
justify
interesting.
the use of generators.
That's interesting. I guess you could also technically use it in a constructive way, right? Like for example, if you want to find the generators of a dihedral group,
Mhm.
like you could probably just like because like yeah, because the dihedral group is generated by the free group where you have like R F, where like but then like if you import like you have R to the n equals to F2 to the equals to the identity,
Mm.
then because all the F's are just generated by some R composed of like the base F, like the rest of the flip. So like, oh, that kind of makes sense. Yeah, that kind
Yeah,
of makes sense. So you can use it to find the generators of that dihedral group.
yeah.
That is interesting. That's interesting.
Yeah.
That's interesting. That is really interesting.
So
Interesting.
any
That's so
commutative
interesting.
monoid. The reason why I want to study category theory, because it seems to be needed to understand more like my it's actually starting to limit my physics. Like
Really, that's kind of interesting. I did not know category theory limits physics.
yeah, it kind of is I'm currently trying to study let me think. Uh well yeah, I'm currently trying to study some high power topics in Lie theory,
Okay.
like the Lie. Let me think. Representations of Lie group.
Yeah.
Representation of compact Lie group. There's like that.
Okay.
Let me.
What is
Can't
what's the
recall.
representation here?
Representation is a homomorphism from a
I mean,
group
the general
to
linear, right?
to general linear. That's right.
Oh, that's the cover. That I think that picture's the cover of my math textbook.
Mm.
Yeah, E8, right? Yeah, this looks like E8 category. Oh, well, maybe it's just under representation theory on the right side. Oh, Lie groups in physics. Interesting.
Root. There's notion of roots and will and let me see. Okay, so we get to this Lincoln diagrams.
Yeah,
Coseta groups. Yeah, I do. Oh, I think I know. I think I know. It's okay. I'll just show you what I'm trying to study
sure.
recently.
Conformal field theory. What is conformal field theory?
Characters. This is the book that I'm trying to understand.
Okay.
Then they're talking about like Verma modules. Okay, I guess it's not immediately my
A
limiting
VMware module
factor.
is a module. Sounds like a module. Module is
It
a
is a module.
vector space generalization where you think of a ring instead.
But if you search things like Bruhat, like here they mention Bruhat order, right, and stuff.
Yeah.
Bruhat order. I'm pretty sure I'll get some categorical
Coexter group. I feel Bruhat Tits building.
yeah, and then
Um,
you talk about this and how Schubert varieties. I mean varieties, they are starting to get to algebraic geometry,
hmm,
right? And things like this.
interesting.
I feel like
What?
I need to know.
The real question is how does Wikipedia have so much random ass math? Like what the heck? And these are really
Yeah,
detailed too.
yeah, they're pretty good actually.
I mean, I did see one really bad one, which is called a compact set closed.
Oh,
Yeah, but like, I mean, it would be fine if you have like a compact space, but then because like if you have a closed set and a compact space is obviously gonna be compact, but like if you like they use the example of R2, which is definitely not compact. Like closed set R2 is definitely not compact, not necessarily compact. That's for sure.
yeah. Anyway, I think
What's the point of this conformal field theory thing?
okay. So conformal field theory is a theory where there's no notion of scale in the theory.
Okay,
Yeah, and it turns out it's very important in physics because at least the reason why I'm trying to study it is because a string
yeah,
it traces out a sheet in time, right? Like if you take a string and then you evolve in time, it traces out something called world sheet.
yeah.
It turns out it's useful to analyze the world sheet itself. And the
Mhm.
world sheet theory is a two-dimensional conformal field theory.
What is field? Okay, what is field theory? Like,
Uh, okay, so roughly speaking, a field we learn in physics that every point in space has a potential, right? Potential energy, GPE, right? So
sure,
that way you're associating every point in space you're associating with some real number, right?
sure, yeah,
Then we learn there's an electric field, which is a vector field, meaning that every point in space
It's a vector. Yeah.
we associate with a vector,
okay.
R3 in this case.
This is incredibly
Then
confusing because none of this sounds like the field in like
yeah, it's different. It's a
thing.
completely different thing.
God damn it! Why? That's so abusive. So, could have
Uh,
something different.
and then
Yeah.
so is in conformal. So field theory is a study of how these fields evolve with respect to time. So they'll
I feel like
usually
most of these fields are going to be represented as like some kind of differentiable manifold.
um that at higher level, yes, eventually we actually have theories where the element of the every point in space gives you an element of, let's say, some Lie group G, right?
Which is really just a
Which is
differentiable manifold. Yeah.
yeah, or perhaps they can be even so these are if every point in space gives you an element of some manifold M,
All
it's
right.
known as sigma model.
Okay. Oh, this is interesting.
Yeah, so you search non-linear nonlinear sigma model. This is used in string theory as well. So
Okay.
so as a result,
Ooh, that's interesting.
yeah, it's some nice stuff. So for example, to describe
Nice. I love how I love how y'all found out the use of all the useless math.
usually there's a lag of 50 years. So
Yeah.
yeah, maybe today we're learning about today
Wait,
mathematicians
hold
are
on. The
developing.
quotient space is a manifold. Wait. This is usually not. This is usually not. This is usually not. This is usually not true. How? If G is a Lie group and H is a Lie subgroup, then the quotient space is a manifold. Oh, this feels like it's something really useful actually. Because most of the time, a quotient group they behave so poorly. Like
Mm.
yeah,
Uh,
it behaves so poorly. Quotient groups always behave super poorly, but
but
quotient
if H is if the subgroup is a normal subgroup, then it's okay, right?
yeah, I mean, I guess it's a D group. As
Lee
in,
sub,
you can only quote H has to be normal because you cannot quotient if it's not normal.
yeah,
Yeah, in groups, yeah. But
Lee
as in
subgroup.
because usually like if we like usually if you do like because if in general topology, right, if you quotient you don't always get a manifold out. Yeah. Like
Hmm.
in fact, most of the time you do not get a manifold out. Like the classic example is just like view line with two origins.
Hmm.
Yeah, like that. I that thing is so cursed. Like yeah, but yeah, like you usually don't get a manifold out. But yeah, this looks like a really nice property. Like if
Hmm.
G is a Lie group and H is a Lie subgroup, the quotient space is a manifold. I would
Hmm.
love to see the proof of that, honestly. Like
I
that
see.
just this seems like such a nice property. Yeah.
Hmm. Well, I I could give you
I'm
an
sure okay, I'm
example.
sure I can find it in a math
Hmm.
textbook though. It's in the Lee Riemannian manifolds book. Unless you have a proof that you want to present that's like kind of short.
No, not
Oh,
really.
no, it's not kind of short. Was
No,
it?
no, I don't really know any proof.
No, you don't know proof. Okay. But I mean it does seem it feels like a nice property. Hmm.
So things like sigma models, they are useful to describe things like ferromagnets, right? If you have an array of ferromagnets,
Okay.
Heisenberg model, if you have an
Okay.
array of ferromagnets, then let me see this nice picture. You can kind of think of it as this an array of magnets. So magnets have an orientation to it.
Right.
Yeah,
Oh, so
so
you can think of the magnetic field like a manifold, like the strength of the field
yeah. So you
as
can
like a
think of
sort of manifold.
the
Okay.
something
Right.
like
Right.
that. And things like that, basically. Every point in space, this is a 2D one, and every point in space you
Yeah.
have a small arrow. And you can tell if the arrows at two different locations, right, side by side, is opposite directions, maybe that's lower energy. If they
Yeah.
are the same direction, maybe that's higher energy. So
Okay.
then
Yeah.
you're asking questions like what is the lowest energy of all the configurations? You want to find the lowest energy configuration among all the
Okay.
many
So
possible.
this feels like taking like a tangent uh like is it like differentiating on the manifold or something and then
Um,
is it I don't even know what I'm
it's kind
talking
of
about.
like finding the global minimum,
Right. Right.
kind of like finding a global minimum of all the possible orientations of
So
points.
this has to be taken over a Lie group, I'm guessing.
Uh,
Or like can it be any manifold?
actually the orientation of the spins don't even need to be in some continuous group. They can just be up or down.
Okay, yeah, as in like I mean as in like do those like fields, do they need to be like in a differentiable manifold or can it just be any manifold?
They can be any.
Oh, that's interesting. So you have to find a global
It
on
could.
a
I
general
mean,
manifold.
the icing model on here is up or down. So it
Mhm.
doesn't even. It can. This is a discrete, right? It's either
Yeah,
Z2, either up or down.
yeah,
You don't even need um you don't even need it to be
yeah.
continuous like
R,
that.
yeah, sure. I
So
mean, you
so
could probably extract R2, like you could probably extract Z2 out of like in like some cursed way by like defining some equivalence ratio R, like maybe just take like the lower half, like all the negative numbers,
we
and then
say Z2 because there's flipping symmetry, meaning that if all the spins are flipped
yeah,
from bottom to up and from top to bottom,
mhm.
right, then the entire system has the same energy.
Okay,
So that's what
right,
we mean by Z2, in the absence of an external magnetic field.
okay,
So so the reason why we want to find the ground state energy, and this is a hard question, it's like
mhm.
finding the ground state, the lowest energy configuration is
Right,
akin to like in like machine learning, you want to find the global minimum. That's
yeah, sure.
the same problem.
Yeah, they just ready to. I'm guessing it's so like it's not always possible to find the global minimum.
You might find a bunch of local minimums, but
Right.
but we want to find a global minimum because nature naturally goes down to
Nature has a global minimum.
nature
We just can't find it.
nature is like this giant parallel processing computer that just automatically finds the minimum,
Right.
and it's our job to find the minimum because
That's interesting.
if you know the minimum, you can find excitations of the minimum.
Yeah.
And what happens if you shoot it with a photon? Like
Mhm.
it goes from a lower state to a higher state or something. You
Mm.
bombard it with some energy. You put temperature on it. Like you can find out what other energy, how the properties would change over time. And there's also an interesting point where if you take the temperature of this system
Sure.
and you raise it up to a certain point, you
Mhm.
get to a point where because the rule of temperature is average energy.
Yeah, that one I know.
So if you increase the temperature of this system, right, roughly speaking, you are saying that these guys they can be at a higher energy state.
Mhm.
Like so it won't it at zero temperature, right? 0 kelvins,
Right.
you'll find the true ground state, theoretically at least.
Right.
But if you raise the temperature, it'll go to higher and higher energy states.
Okay.
And that also means that there's a point in turns out it's a fact of experimental fact that when you raise it past a certain temperature, right, you hit a critical point, critical temperature where like if you hit a critical temperature, then the entire behavior of the system kind of goes from one phase to another.
Okay. Yeah.
For example, initially, okay, let me see icing model phase transition. Icing model phase transition. It is
Right.
nice picture. Okay, I think there's a nice video to show this.
It was long to just send it to me.
Uh, there's a nice animation.
Lol. Animation.
Yeah, like I think
Is this like this is like some string theory thing, right? Like, or like is it just
no, it's in general physics.
okay, right. So
But
like
I mean, it appears in string theory as well. So
okay, yeah.
yeah, I can't really find a good picture for it. Critical phenomena phase transition. Um, I wanna show correlation length.
I'm guessing this is somewhat related to like those weird ass oh, here's CO2 becoming super critical thing.
Yeah, it's all related. Statistical physics,
Oh.
critical phenomena, critical. There's no nice animation. I know I'm very sure I saw a YouTube video on it, but
Okay.
it turns out that at the transition points, right?
Right.
Maybe I'll draw something. So initially at a low temperature, maybe let's say T equals to 0, right? You have basically the regions look something like that. Very huge regions, right? The regions where they are up or down. Right? Let's say
Okay. Yeah.
you can see clearly all the domains, like where they separate, kind of.
Yeah.
Then as you raise the temperature, right? Maybe you say this is T equals to 50 Kelvin, then
Sure.
maybe the domain walls get smaller, right? I mean the domains get smaller, the regions get smaller.
So like the different states.
Like there's a whole region where all the spins are up. That's what I define as a domain.
Oh, okay, right. So like okay.
So as you increase temperature, the domains get smaller and smaller. Right? If you raise temperature to very, very high temperatures, let's say 10 to the 5, then basically
The domain is
domains are super fuzzy. Everything is like it's just white noise basically. So on one end you have very ordered.
infinite temperatures, the domain just continuous or
No, it's just white noise. It's like
this is
every pixel is every location is very uncorrelated with the next one.
okay,
basically.
yeah.
So basically
Okay.
at one point in time, the correlation, if you take like the guy at
You see how this thing evolves, I'm guessing.
yeah, how it evolves as you change the temperature. So if let's say over here we take the correlation of a point X with a correlation of a point Y,
Okay.
right? Maybe you'll get something like we might get something like uh some dependence on how X and Y are separated. So if X and Y are small, right? If X and Y, if the X minus Y is small, they're very close together, then they'll be highly correlated. If
Sure.
they're very far apart, then they'll be very poorly correlated.
Okay.
So we might be expecting something like 1 over
Mhm.
this, where if they're small, right, then it's very high. This is the correlation function
Yeah.
relation. So this measures how correlated it is. A high number would mean that if we know phi of X, we know pretty sure that phi of Y is going to be around
Okay,
this.
so for example, okay, so wait, let me get the board. 1 sec. Let me move over. Try to find the thing. Okay, we are at over here. Okay, so like for example, like if let me grab a pen with a yellow color. So like for example, these like for example, a particle here and a particle here, these are very correlated, right? Whereas like a particle here and like a particle here are not very correlated.
Yeah, exactly.
Okay, right.
Yeah. And then at a very high temperature, phi of X and phi of Y,
Mhm.
right, the correlation is basically zero, right?
So like nothing is related to anything else.
Yeah, nothing is related to anything. Every guy is just
Why?
independent. Because energy kind of you have provided enough energy such that
Is there
that
something to do, like the interactions between the particles?
yeah, in some sense uh like you at high temperatures, higher energy states
Mhm.
are possible to exist. Like the higher energy states, they're more statistically favorable to
Okay, yeah.
exist than at lower energy. So like here, right, maybe if this guy is like that, he'll induce the next guy to be like that as well, because
Yeah.
this is lower energy.
Yeah.
But at a high energy, it doesn't really matter because you have enough energy, you have enough, like you can think of temperature as a energy as a currency. You have enough currency to afford to be completely independent of
Yeah, okay, I get it. So
yeah.
I'm guessing this correlation, like this function here, I'm guessing is some like thing that's like dependent on t, right?
Yeah.
So like you
Correct.
could have like maybe like it's like maybe you have like some functional that operates on your correlation function. Oh gosh, why is everything such a straight line? How do I like, okay, I have to use my trackpad. So like this thing, and then like it's like dependent on t or something. IDK, it's like this thing like evolves based on time and it transforms your f or something.
Hmm.
I'm just guessing, like I have no clue how any of this works. So
F is the correlation, is it?
yeah, so f is like the little f is correlation. The big F is the thing that transforms the correlation function based on the temperature or something.
Yeah, we can kind of think of it as that.
I'm
Yeah.
I'm guessing that's probably not what it is, but in like I don't know, because like firstly it's probably not even continuous, but yeah, is it continuous?
It's continuous until we reach the transformation of the correlation function as temperature increases. It's basically continuous
So,
until the transition temperature.
okay,
Yeah, at the transition temperature, that's where uh
continuous and differentiable, I'm guessing too.
yeah. So okay, so that's roughly it. And but the interesting thing is that at a critical point, right?
Mhm.
Critical point, the correlation length is actually infinity.
Huh. Okay.
So that means that
Huh.
okay,
Okay.
wait, correlation, no, sorry. Okay, the correlation, it becomes independent of the distance. Okay,
So
sorry,
it
the
no longer
correlation
depends on.
is just some constant c perhaps,
Okay. This is okay. That's weird.
independent of x and y. Yeah, that's weird, right? Because
That's really weird. Yeah.
it's really crazy because that means that point here, right? So the correlation length is
Yeah.
roughly speaking
So
how
the
far.
same. Yeah. Right. But like, so maybe it's a point here. Like, so maybe it's like a point here and a point here. Like, they are just as correlated as a point here and a point here.
Yeah,
Like here. That's
exactly.
so weird. That's so
Yeah.
weird.
So that's the thing that actually is
Is this like some open problem or something?
yes, actually in fact
Oh,
this there
okay.
is quite a lot of
Yeah.
open problems in
That
the
does
field.
that. I mean, that does seem weird as hell.
I can show you I can send you videos when I come across it. Uh Let me see.
The Quanta, freaking Quanta magazine, bro.
Critical math.
Critical maps. This guy just pulled all maps. I hate this. I hate those two things.
Critical.
You can just link me the physics one, I guess.
Okay, I can't find the videos that I want to talk about.
Why are all the recommendations so garbage, Lamau?
I'll send you if I find
Okay,
any.
sure, yeah,
But actually this is
that is really weird. That's really weird.
crazy, right?
Yeah. In fact, I don't even okay, honestly, the zero thing is also the one that kind of like boggles me a bit, because it's like, what the heck? Like, surely even if it's at a high temperature, there's supposed to be some relation, right? But really just not at all.
I would say that as the limit of t goes to infinity,
Okay.
it'll be just white noise lah. Yeah.
Yeah, of course, as in.
The crazier thing is over here where, I mean, at low temperature, it makes
Okay, yeah.
sense that closer guys, things that are closer are more related than
Yeah,
things
that
are
makes
further
sense,
apart.
yes.
The things at high temperature kind of make sense that even if you're very close, okay, maybe like I'm not sure if it still follows the same x minus y to the some
Right.
power. I'm not quite sure. I should get checked on that. But the crazy thing is that at critical point, at some particular temperature,
Okay.
whether you and your neighbor are correlated, your immediate neighbor versus you and some other far away guy correlated, is completely independent of how far you are separated. Meaning that
Yeah.
statistically, that just sounds wild, because
That is so weird. That is so weird.
because remember the interactions are only happening at local regions,
Yeah.
meaning that
Yeah.
your whether your energy is affected, your energy level is only affected by whether your neighbor is
Yeah.
up or down. Or
That just feels really strange. That feels really strange.
Yeah. So it is a nice balance where, so okay, actually there is that. So remember how just now I said that conformal field theory
Yeah.
is a study of few theories where there's no notion of length.
Oh, so that's why they're trying to figure this out?
Yeah.
This
so,
thing.
So if there's no notion of distances and scale, right?
Right.
Then that kind of makes sense. So basically, conformal field theories, they are a very good candidate for describing critical phenomenon at a critical transition temperature.
What about like for everything else?
So it's more like okay, so all of these three are studied in statistical
Yeah, StatMech.
StatMech, right? StatMech. And
yeah, I know that joke. There's that one r/textbook humor meme. Have I sent it to you before? It's really funny.
I don't think so.
Okay, let me send it to you.
So all these are studied under StatMech. And we know that at a critical point,
yeah,
this happens. So we're just trying to understand the critical point a bit better.
Yeah.
And actually questions for why we want to, I don't really know why we want to study critical point so much.
What? Okay, I'm still confused. What is the critical point exactly? Like,
critical, you can just think of point as temperature, basically. The
okay, yeah.
critical
So what
temperature.
is this critical temperature exactly? Like,
Or what is it in real life?
as in, okay, what is it defined as here? And then maybe you can give a real life example if it helps.
It's defined as the boundary between different phases of matter. So phase diagram. So for example,
Okay. So like at this point, everything is this, right? But like for example, at 0 Kelvin, there could be like things that will be a so-called solid, and also a liquid. Like as in there'll be solid and liquid the same thing. I don't know.
They will be yeah, they're kind of both phases they're kind of both phases.
Okay. So let's so like this thing's at 0, right? So like what do these boundaries, like these black boundaries here, what do they represent? Like I'm drawing highlighting blue.
Okay, they usually represent points where like your like, let's say if a liquid, right, that's boil just trying to boil. So they represent, you know how you put heat into a water,
Yeah.
when you monitor the temperature, it'll reach a certain temperature,
Okay, yeah.
and then it's gonna stay at the temperature
Okay,
until
that
all
makes
of it turns into gas.
Okay, so like basically also some of the things are taken to gas, and then the boundaries are just like expanding until it all becomes gas.
Yeah. So like it's like you can think of it as like the lines over here, they are points where like half of your volume is in gas phase, half of your
Okay.
volume is in
Right.
yeah.
It doesn't necessarily have to be half, or like as in like it's the thing is
Or
just
like there's a proportion. There's a
okay, yeah,
proportion.
okay.
Depends
That
on how
makes
much
sense.
heat you put in. Like it doesn't instantly all turn into gas and
Okay,
whatnot.
right.
Yeah.
So what does the up and down have to do with it though? Like
Oh,
go to the whiteboard thing, right? Like
that's
I
just
highlighted blue, right? Because this is at 0, right? So surely like things at 0 are going to be like a solid, right? That is a solid, so like up and down. Like how does that
uh,
have to do with it?
oh no. Actually, I was referring to the other one over here.
Okay.
I thought you were referring to the
Oh,
boundaries over here.
oh
But
yeah. I was referring to
just
that, and I said the whiteboard, the blue thing. Like why? As in things at 0 are definitely a solid. So why? What's the distinction for like?
so this okay. No. Actually, just now what I described was um just now what I
What
described was
about the
the
transforming
difference
of like things into?
between different phases of matter.
Yeah, I
What I
know that.
described
But
was
like, yeah, but like, why is the critical temperature so interesting?
these are just domain. The one that you highlighted in blue, they're just called
Yeah.
domain walls.
Okay, sure. So like
Nothing.
it's just when things go from like up to down and whatever.
Yeah, basically.
Sure. Yeah. Then what about like? But what about the critical temperature? Why is it like?
Uh, so the critical temperature is is a transition between like the ordered phase of
Okay.
this system and the disordered phase. So
Okay.
at the critical,
Let's say like T goes to 25. Would that just be more domain walls, but you can still see them? So at what point does it become like unordered? Is it like when like the domain walls are like between every single particle, like there's a domain wall or something?
uh, in some sense, it becomes
Or you're gonna say like
um
the
the
measure
defining the
converges to
defining the defining temperature. The defining property of this critical temperature is the infinite correlation length. Is this property that I described here?
okay. So like there's no like,
This is of our
defining
greatest
limits on
interest.
that thing. Okay.
Yeah, this is
Right.
of our greatest interest. There are some corresponding quantities that diverge. So, for example, like the heat capacity at a critical point at the transition temperature, the heat capacity
Oh,
becomes like
the heat capacity of
large.
fluid becomes infinitely large.
Yeah, meaning that
Wait, that's so weird.
so at the critical point, a bunch of stuff happens like
Okay.
um
Oh, so it's like the super critical thingy.
yeah, it's supercritical is kind of related to it also.
That
There
that's
are some thermodynamic quantities like 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 heat capacity or like
heat capacity being infinite is so weird.
which what that means is just that if you raise the temperature a bit,
Right.
you put heat into the system, the temperature of the thing doesn't um well it's kind of like it's going between one phase and another, and the heat capacity is only well defined in each of the phase, kind of.
That's so weird. That's so weird. What the freak? Why is this so weird?
Yeah, funny stuff happens at the boundary between different phases of matter.
That's so weird. I thought you guys like infinitely differentiable and integrable functions, But like this is so weird. This is really
But statistical quantities, they're not they're usually not. So like the second derivative will vanish or things like that. Like
okay. Yeah.
So like
That's weird. That's really weird.
yeah, it's kind of so if you consider the graph of heat capacity, there'll be a divergence at some point in time.
Like it goes to infinity somewhere.
Yeah.
That-
I don't.
If heat capacity goes to infinite, how can we boil it?
Mm,
Oh, then we're heating the thing we're heating the thing that's like after it boil off. Okay, that kind of
yeah, that actually makes sense. So yeah, actually exactly. You know, in primary school we learned that the temperature will go and then
it stops.
plateau,
Yeah.
right?
So this is where the heat capacity is infinite. Yeah.
Yeah. So it's actually not unintuitive at all.
Afterwards, the heat can still increase anyway, even though it's infinite because we're not boiling that thing. because
Yeah,
it's
kind of.
gone. We're heating up the other thing. Yeah.
Yeah.
Okay, so it doesn't break anything. So
it kind of still makes sense. Yeah.
yeah,
I think the crazy thing is this transition temperature
yeah
and
that one is still weird. Like,
the conformal field theory
it doesn't make sense. Like, oh, we're related. Not anymore.
can.
Yeah, that just feels really weird. Like, it feels morally wrong.
Right.
Yeah,
Um.
it just feels morally wrong. Yeah.
So applications they can be analyzed.
Mm.
Conformal field theory can be used to study these systems, quantum phase transitions and stuff.
Yeah, that's weird. What's supersymmetric Young-Mills theory? Oh, I know Young-Mills is like some freaking Millennium Prize from. It's actually one of the less known ones, I think.
Yeah.
So all the well-known ones are all the ones that are all cranks, Riemann hypothesis, PNP,
CFT.
Navier-Stokes.
So this is something in physics where it turns out that a gravitational theory in some region of space, roughly speaking, hyperbolic space.
You're about to tell me it's NP.
Uh, so
Yeah.
basically, it's hyperbolic space. You can kind of think of it as hyperbolic space.
Hyperbolic geometry.
Yeah, hyperbolic geometry. Gravity on hyperbolic space is actually, in some sense, dual. It's actually described by a conformal field theory on the boundary, living on the boundary. So
What is the boundary here? Is it the same as the like a topological boundary?
Yes, it
Like
is.
the intersection of like I can't believe. Oh yeah, it's like the topological space set minus the interior and the exterior, like that boundary, right?
Yeah.
Okay, sure,
Yeah.
right.
So yeah, I don't know enough of this, but apparently it's really beautiful.
This is weird and freaky.
Yeah. So the nice thing about this is that
Yeah.
a strongly interacting theory in one of them, it actually corresponds to a weakly interacting theory on the boundary. So like strong becomes weak and weak becomes strong. So
Weird. That's very weird. Okay.
but that's nice because if we study like strongly interacting stuff, they are usually harder to solve. Like free theories are easy to solve because the equations of motions are like linear and whatnot.
Right. Yeah, that makes sense.
And then if the free theories have equation of motions that are linear, you can use linear algebra, right? You can use Fourier and all those kind of things.
Yeah, nice, right? Yeah.
And then usually what happens when there's a small interacting term is we basically tailor expand.
Yes, that's where you get the habit of dropping all the OX cube terms.
Yeah,
and then...
correct. So that's where we drop like the higher this is known as perturbation theory, where we assume that the interaction term is weak, right? And then we tailor expand in terms of that. But this doesn't work if the term becomes bigger and bigger. So strongly interacting theories are hard to solve.
Because they get bigger.
Because we cannot apply perturbation theory anymore.
How the frick do you have but I'm still wondering how the frick do you get the Taylor series that increases? Because by definition, that doesn't even converge that function.
If the perturbation is if the x is small, it's more like
like it's about the x, as it still converges anyway.
It's more like e to the what it looks like is e to the lambda. E to the lambda in some terms over here.
Yeah.
Then we Taylor expand this as as 1 plus lambda squared over 2 and so on. So if lambda is small, then this is a good approximation, right? Lambda is a parameter.
Yeah. Okay, yeah, the
parameter for the interaction, for the strength of the interaction.
Yeah. Okay, yeah. Sure. So like but like if lambda is small, then like the x, then like after those things, like those actually become significant enough to look at.
Yeah.
Yeah, that makes sense. I thought it was like, I thought like the terms in the series are growing. There's like, what? That wouldn't work.
Oh.
As in you meant like evaluated at those numbers, then the terms, then it becomes big if you like delete like the behind stuff. Like for example, you plug in like lambda equals to like 1 over like 1 billion or something. Yeah, then that kind of makes sense. Yeah. Yeah, if you put in like 1 over 1 billion divided by 2 or something. Yeah.
So if your lambda is if the exponential interaction becomes big, then the Taylor series would need to consider more and more.
Okay, yeah.
Yeah, and at some point in time, it becomes computationally like this actually the Taylor expansion relies on no actually wait it yeah we need more and more terms, and basically it's harder and harder to solve. And in fact,
Why do you even use Taylor expansions? Like,
the reason
oh, it's
why
because not everything is a nice and analytic. Yeah, I'm guessing.
we use e to the lambda because this is just like it's related to how time evolution happens.
Oh.
It's usually an exponent.
Yeah.
Yeah.
I'm guessing because not all your functions are analytic, so you can't like. Yeah, but it's not analytic. Can't do that. As in, I'm guessing not all of them have like nice like easy easy solutions or something. So you just use Taylor expansion.
Not really. It's just the equation of motions tend to be solved with exponentials.
Okay.
Time evolution operator is an exponential. That's pretty much it.
Right. Okay.
Yeah. So yeah, I should really study this more.
I don't. Yeah, because I still don't get why the freaking sine of x equals to x thing. Like.
Oh.
Okay. So why the frick is sine of x equals to x even used as approximation? I feel like sine of x is a perfectly nice function. Is it not? This
Yeah,
is the of that.
we don't really use sine of x. Yeah, we don't really use that much.
Oh, is it? Or do you just use like the e to the I something definition of sine?
Yeah, we use e to the I more than we use sine of
I mean
x.
that's the nice one anyway, because like x is complex analytic. Yeah. So. Yeah. Okay.
Yeah. Anyway, yeah.
I really don't get the sine x equals to x meme. Like, what the heck? Like, as in, it's still really funny because.
There's more of engineers because they like the pendulum, right?
Yeah.
When you
The
have a pendulum,
the sine thing. Are they doing like integrals on the thing?
yeah. So if you have a pendulum, then your equation of motion looks something like second derivative is minus g over L, right? This.
Yeah.
But actually, this is not g over L. It's actually sine of theta.
Right.
So this, if you consider this, is non-linear differential equation.
Oh, so it's a pain in the ass to integrate.
Yeah. It's actually still possible to solve using the elliptic integrals and stuff, but
there was like there was a this thing called like SI a sine integral. What's this thing? Like from Wolfram. Is it like the non-closed form one? Let me find it. The sine the SI the sine function integral thing. There's a lot of like sine x over x that you need to integrate, and then you can't integrate. Yeah, because that doesn't have a closed form. The integral of sine x over x. Yeah. So that's, I guess that's why they're turning into x lol.
Yeah. So okay. Anyway, yeah, I think I'm probably gonna go.
Okay, sounds good. I was only going to shower. It's very hot. Okay.
Yeah.
Cool.
Okay.
Nice
Thanks
talk.
for the nice talk. Yeah.
Thanks. Bye bye. Yeah. See you.
Bye.
Bye.